Thank you, everybody, for joining this Agent-Based Models for Generating Synthetic Data training workshop. My name is Dr. Jools Kasmire. I work with the computational social science training team at the UK Data Service. A brief table of contents. This table of contents actually matches what's in the slide deck, and you can get this slide deck through our events webpage after the workshop is done. A little bit out of order for what we'll do in the workshop. We will cover what is synthetic data. We will cover top-down versus bottom-up, agent-based models. We will look at examples, pros, cons, tools, and next steps. But the live demonstration and discussion will actually come between the agent-based models and the NetLogo examples. That's because this is a long workshop. We want to give it a bit of a break. So we'll have 10 to 15 minutes, just sort of an intermission, let you stretch your legs, get a drink, make a phone call, whatever it is you need to do. Getting started with the topic. What is synthetic data? Maybe you don't. Maybe you don't know. We're here for it anyway. The key point about synthetic data is that it is generated, not observed. So there are many ways to generate synthetic data, and there are many ways to observe data in the real world. But the difference between synthetic and real world data is generated, synthetic, observed, real world. So a key point related to this is that a responsible generator of synthetic data would double check their synthetic data to make sure that no lines of synthetic data match any observations of the real world. Depending on what kind of synthetic data you have, it is theoretically possible that you could generate a line of synthetic data that is very, very close or indistinguishable from a line of real world data. You want to be careful to not do that. Related to this, it might help to think about predictions. So if you want to do a weather prediction or a stock market prediction or any kind of prediction, that would be synthetic data because we cannot observe the future. At least not yet, not with any of the technology that I have access to. But something that people always talk about with synthetic data is fidelity. Now, fidelity is faithfulness or the similarity between synthetic data and real world data. Now, we obviously know that they cannot be exactly the same because that's irresponsible, but they want to be similar. So that gets a little bit strange because like how similar is too similar? What do we call it when it's very similar? What do we call it when it's vaguely similar? So that comes down to fidelity. So fidelity can never be 100%. That's too similar. We can't be having that. But more importantly, fidelity doesn't always apply because not all synthetic data is generated in order to specifically mimic real world data. Now, you can just make up random numbers, for example. That's not matching anything in the real world. There's no fidelity there, even though making up random numbers is generating synthetic data. But it's also, if you generate synthetic data and there is a real world data set to match it to, it's not a binary high or low or similar, dissimilar. It can be very, very similar in some ways and very, very dissimilar in others, the same two data sets. So we have to think about, is it structurally similar? Is the content similar? Are the relationships similar? Are the means similar? Are the distributions similar? There's all kinds of different ways. But it's also important to think about higher fidelity, so more similar, is not always better. For example, if you're trying to test code, you want to know that specific certain errors are in your test data, even if those errors have never actually been observed in real world data. So that's a dissimilarity that we want. Likewise, if our real world data we know is missing a population, we want to generate synthetic data to sort of fix that gap. That's a way that we want our synthetic data to not match the real world data. However you have generated your data, however high or low its fidelity, It needs good documentation so that people know whether it's high or low, whether there's a real world data set it's trying to mimic or not. This is important. But enough about that. Let's talk about generation methods. So uses on the left-hand side and generation methods on the right-hand side. This is a short and non-exhaustive list. And for both of these lists, sort of simpler, faster, lower fidelity options are at the top of the list. And at the bottom of the list are sort of higher fidelity, more complex, more time consuming kind of methods. So preview data, you might have just one or two lines and they're obviously fake. Whereas if you want to work remotely with people who don't have permission to access a real data set, you're going to have to spend a lot of time making a synthetic data set that will work for the kind of research they're doing. Likewise, you can imagine something just in your head, just make it up. And that is a quick and easy, fast way to make up synthetic data. Whereas if you want to build an elaborate digital twin simulation, that is a much more complex, time-consuming way of generating synthetic data. Now, we won't go too much into this because this session, is about agent-based modeling, and that is a kind of simulation. We will also talk a lot about machine learning because it is a relevant, sort of comparable kind of synthetic data generation method that I want to compare and contrast with simulation for the purposes of this workshop. Now, getting on to our first Mentimeter interaction, so please join at menti.com and enter the 8-digit code at the top of the screen. Are predictions synthetic data? I have covered this. Hopefully you remember. Yes, we've got some people who have paid attention. Yes, for the most part, like as far as I can tell, excluding any kind of time travel, predictions are always synthetic data. They are generated by some kind of method. So a regression model, a more complex machine learning model, some kind of prediction, some kind of made up out of our head. But they are predictions rather than observations. Got another one. Does fidelity apply to all synthetic data? Again, I've given you a yes, no, and a not sure option because you can never tell how people interpret things. Sometimes questions can be a bit vague. Yeah, I would say fidelity does not apply to all synthetic data, mostly because not all synthetic data is made using or based on or in an attempt to mimic a particular. It's entirely possible that all of the synthetic data that you have used, fidelity does matter for that. So it's an easy sort of one to misinterpret, I think. Finally, is higher fidelity always better? Ah, people have been paying attention. Thank you very much. Yes, there are some cases where we specifically want our synthetic data to look unlike the real world data. And in that case, it's specifically a lower fidelity. And I will grant you that I need more information is not wrong because these are specific cases. In general, most people agree that higher fidelity is better in terms of realism, but it's not always better in terms of cost effectiveness, ease of use, ease of access, time consuming nature of construction. There are reasons to want low fidelity. That's all I'm saying. Now, moving on to top-down versus bottom-up. Systems can be top-down or they can be bottom-up. Most of you will probably have heard of top-down. We talk about top-down reorganization in a company, for example, and we're all aware that a change, for example, in an organization can be decided at a high level. And, the people at the high level tell the people that just immediately below them about this change, and they tell those people, now you have to cascade that down. You have to tell the people below you, and then they have to tell the people below them. And the change moves top down. You may have heard of bottom up, but if you haven't, you've probably heard of related terms like grassroots or groundswell or emergent. These all capture sort of the reverse. These are the changes that happen at lower levels and that become sort of self-reinforcing and popular and powerful until the change drives upward. So we're talking about change within a system And a system can be top down or bottom up or a bit of both, depending. And a top-down system will tend to have top-down change, and a bottom-up system will tend to have bottom-up change. It's never 100%. Likewise, problems can be top-down or bottom-up. So a top-down or a mostly top-down system will have mostly top-down problems, and a bottom-up system will have mostly bottom-up problems. Again, nothing is ever 100%. But many systems are mostly one or mostly the other. Let's look specifically at top-down. Now, systems or problems are top-down if they are whole, well understood, have central control or a centralized structure, if they can be broken into defined parts and interactions, if they work with classical scientific method ideas of isolation and prediction and repetition. Now, remember, nothing is ever 100%, but some classic examples of top-down systems are engines and hierarchical organizations like a military or a company. Hence why I chose this picture, because it has both military people and an engine. Now, engines and military units are generally well defined because they have a list of parts or a list of staff members. And those parts or staff members are also well defined because they have ID numbers or, staff member names and ranks and titles and defined responsibilities, things like that. And control within these systems comes from the top down. That is, there is a few predictable, limited number of decision makers or starting points that initiate the action. And if you get a problem in these systems, you can take them apart, you can replace one of the people or one of the parts, and you can put them back together, and you can test if the replacement had an effect. So these are top-down systems. In contrast, bottom-up systems are poorly understood, have open or flowing boundaries. They have partial or decentralized control. They cannot really easily be reduced to parts. They have emergent behavior. They don't work well with the classic scientific method, and they are best understood through simulation or modeling. So a classic example of a bottom-up system are ecosystems or traffic. Now, these are not well defined in that they don't have clear edges. Where does traffic stop? Where does an ecosystem end? There are no parts list or staff members list, because traffic today is not going to be the same as traffic tomorrow. It's going to have different people in it. Things come in and out of them all the time. There are bits that are sometimes seems like they should be part of the system and sometimes not. Maybe that would include migratory animals for an ecosystem or lampposts for traffic. They're not usually a part of traffic, but if someone accidentally crashes into a lamppost, it suddenly becomes a part of traffic. And there's no centralized control in these systems. So, there are laws and there are traffic lights, but people don't always behave like those laws or traffic lights really always matter. And instead, it's a whole bunch of parts that are just kind of interacting the way they interact. And they cannot be delineated or replaced in the same way. I can replace one car with another car, but the behavior might be very different depending on the driver. And, I can't replace one species with another species because it just has all kinds of weird knock-on effects. So they can't be broken down. You can't replace the parts. It's just not interchangeable in this way. You also can't really repeat the things the way you would traditionally with a scientific method. You can't reset it back to the exact conditions at the start and do it again to see what happens again. Pardon me a moment. And, you can't, instead, they're full of context-dependent interactions and emergent behavior. They're really hard to study through the classic scientific method, and instead, a better way is to study them through simulation or modeling, which is to say you try and build a simulation or a model that has the same overall kinds of behaviors, and that gives you a plausible explanation for how it happens in the real world. Now think about data. in these two kinds of systems. How would you get data from an engine or from an ecosystem in the real world? Now, you'd probably think observations and sensors and measurements and these things, and you would not be wrong. But think about how they're different in the engine versus the ecosystem. So are they internal or external to the system? Do they influence the system, or are they just, can they be kind of treated like neutral observers? Do they look at a part of the system of the whole? Are they directly measuring the thing you want to measure, or are they kind of measuring something that you use as an indication of what you want to measure? So, for example, if you have a temperature sensor in an engine, it doesn't necessarily affect the engine's performance, and it does directly give you the temperature of the engine. Whereas if you count the number of birds that go through your garden on one Saturday in April, that's not going to tell you how many birds were in your garden, just how many you saw. And what does that tell you about the bird population? Well, it's just kind of an indication of bird populations. It's not a direct one-for-one measure. So, and then you have to think like, are we trying to measure, like are we checking that performance matches a standard, or are we trying to understand things? So the temperature sensor in the engine is really trying to make sure we're within a narrow window of ideal performance. Whereas counting the birds in the garden is just trying to get a sense of, are there birds more or less than last year? What might have changed or not changed. So that's just a bit about real world data. Now think about synthetic data for these two systems. Would you use the same generation method for both? And it kind of depends on a lot of factors, including how much time and effort you want to spend on the generation method. You can probably guess that I'm going to tell you that you want a different generation method because of the different nature of the system. So a top-down system is probably a very good candidate for a machine learning model. Machine learning is kind of a top-down understanding of a system. So it looks at all the patterns of behavior and it finds like a predictive model that won't go beyond the data points it's observed. It won't do anything weird. It won't do anything new or original or confusing. Whereas in a sort of bottom-up system, you kind of want to allow for weird or original or confusing or sort of compounding interactive effects. And therefore, I would suggest you want a bottom-up method like an agent-based model, which I assume is why you're here today. Hopefully. So, a couple of quick more Mentimeter interactions before I get into more about agent-based models and why they are good for bottom-up synthetic data generation. So have you ever thought about top-down versus bottom-up before? There is no right or wrong answer here. I'm just trying to get a gauge for whether these are baffling new concepts or established concepts that we've all worked with. So, okay, pretty good spread around the center, I guess. So a lot of yes, a bit, a lot of maybes, a lot of no. We've got a couple of other, which, I mean, please do let me know if you want to talk about that other. And a couple of people have used these concepts lots. That's great. This is a good spread. That means there's likely to be a good range of interpretations of the workshop materials, potentially some good questions to ask when we come to the question and answer session. Now, remember, there are no right or wrong answers. What are some top-down systems? Obviously, you could say an engine or a military unit, but maybe you have some other ideas. Maybe some of the topics that you already work on, generative models. Yeah, exactly. Yeah. Okay. Hospital departments, companies, religions, governments, urban planning. Yeah, these are some great examples. Thank you, everybody, for being so engaged with the topic. This is great. Yeah. Yeah, a lot of these are really top down. Ooh, crime. That's an interesting one. I would potentially argue crime is a bottom up, but it depends on your perspectives because as I said, there's no right or wrong. And depending on the perspective or specific interactions you're looking at, even very bottom up systems could be interpreted as top-down within a certain scope. So you'll not be surprised. What are some bottom-up systems? Um, yeah, okay. So here we go. Urban growth, society, fashion trends is great. That is absolutely driving weird feedback loops in surprising directions. That is a brilliant example of a bottom-up system. Protests is a very good one. Dietary behaviors, it really does seem to explore all the weird possibilities. These are some great examples. You guys are fantastic. Yeah, memes, music styles, the economy. The economy is very bottom up, I would argue. Tobacco use. Okay. Yeah, you're really capturing it. The sort of behaviors that come around by in lots and lots of small interactions between people tend to become bottom up systems, or not necessarily people, because ecosystems are interactions between organisms. Right. Fantastic options. Thank you very much. So, what are agent-based models? Arguably, that's what you're here for, right? Now, this slide looks like a lot, and I won't define all of these things on this slide because I then have slides that define each of them coming up. So don't worry if we get to the end of this slide and you're like, wait, I don't know what you're talking about yet. It's fine. But in brief, the big picture is that an agent-based model is a simulated world that has stuff and it follows rules. Within that simulated world, there are objects and agents that also have stuff and also follow rules. Now, the difference between objects and agents can be a bit fuzzy, but I'm going to define them as objects have stuff and follow rules but don't make decisions. They're more like they follow rules that are acted upon them. And agents make decisions or they take actions. Now, we'll get into this. So let's start with the world. So the world, this is a simulated world, can be as big or as small as the modeler wants. So it might represent a country, a school, a cell, just about anything. And these worlds, these simulated worlds, move forward in what are called ticks or time steps. So what they do is it's just the tick or a time step is defined by the modeler as however much time they want it to define. So that could be seconds, it could be minutes, it could be decades, geological epochs. It should broadly make sense for the size of the world. So if you're modeling a cell, you probably want like minutes, maybe days at most. And if you're modeling intercontinental economic systems, you probably want weeks or months or years or something like that. Seconds wouldn't mean as much. And likewise, the cell is not going to last much longer than, I don't know, maybe weeks. I don't know about cells. And the simulated world should contain all the things that matter for that world. So if you're modeling a cell, you're going to have stuff that matters to cells, like electrolyte levels or hydration or, I don't know, organelles, stuff like that. And if you're modeling intercontinental economic systems, you're going to want to model things that matter for that. So stock market prices or shipping times or, international regulations, things like that. And something that's really going to twist your melon is that for each of the agents, their world contains everything that is not that agent. So it will contain other agents. So although we think about it as the world, each agent has their own world that's, unique to them. So it's a little bit, ooh, but don't worry. And the state of the world is more or less the sum of all the things that you can measure in it. So if it's an organ, you might say, what is your hydration level? What is the current age of this cell? What does it have or not have? That's its state. And it follows rules about how to turn inputs into outputs and how to react to changes. We'll come on to states and rules a little bit more. Because next up is agents. These are the defining features of agent-based models. For a good reason, because agents do a lot of the interesting stuff. So the agents, they can represent almost anything that you can interpret as acting or deciding. So if we want to think, we quite often they're people, but they could be households, or they could be companies, or they could be cars, or they could be cells, or continents, or something like that. Whatever it is that we think makes sense to represent as a actor or a decider. So just anything really. Be creative. They have things and they have features. So if I'm talking about people agents, they might have a name or an age or a location or a bank balance or a education level, whatever it is that matters to your research question. They are unique, sometimes only trivially so, and we'll see more examples of this when we come on to the modeling examples. They can be very unique, or they can just have different generated ID numbers, and that's what makes them unique. But they behave uniquely because only one agent can act at a time. So there will always be one agent who acts first per time step, and that features into the world for all the other agents, meaning that every agent acts in a unique time and way. They also have states. So that would be their current age, their current location, their current bank balance. Their name probably doesn't change that much, but it's part of their state. And they follow rules about how to turn inputs into outputs, how to make decisions. And they make those decisions based on their states, possibly their history, their internal rules about, what it is they're striving to do. And agents can also exist throughout the entire simulation, or they can spawn and die. And maybe that kind of regeneration and turnover is part of the thing you're trying to model. Okay. Now, I meant to move this slide. It's okay. I'll talk about it here. So synthetic data, that is one of the title words in the name of the workshop today, so I will emphasize it. The output is whatever the modeler wants to ask the model about. So that could be that it asks the world to self-report, how many agents are alive right now in the world. And they do this at each time step. And that's the output, is how many agents are alive at each time step. Or it could be, what are the stock market prices at each time step? You could also, the output could be asking each individual agent to report their location, their bank balance, their current age at each time step, or every time step, or only at the end of the simulation run. It really depends on the logic of the thing that you're trying to represent in your simulated world. Now, I will grant you, this is all very abstract so far. So let's make it a little bit more concrete by looking at some sample rules. Imagine, for example, you have a city, a simulated city, and you want to explore how people choose to commute to work. So you have a bunch of agents who live in your city, and time steps in your simulated city are 30-minute blocks of time. And the agents represent commuters who have to choose whether they take a bus or a bike to work. Now, even if every single agent has this exact same rule, that if the weather is raining and the temperature is lower than 5 degrees, they take the bus. Otherwise, they take the bike. Now, because every agent wakes up maybe at a slightly different time, and they look around them and they have a coffee and they think, will I take the bus or the bike today? And they look at the temperature gauge. They're going to end up traveling slightly differently because maybe they wake up earlier or later. Again, this is controlled by the modeler, but let's assume they don't all wake up at the same time. But you can also have it so that every agent has a slightly different rule as well as a slightly different wake-up time. So let's say some of them say if it's raining and colder than 5 degrees, I take the bus, otherwise the bike. Whereas really hardcore fitness agents say, I will only take the bus if it is snowing and colder than 3 degrees. So even with these two simple rules, and you could have hundreds of different iterations of these kinds of rules, you would get some agents taking the bus, some agents taking the bike, and you could get sort of different emergent patterns of how they end up traveling that are different every day, even if they're all technically living in the same city and experiencing the same weather. Now, you could probably get the same output. So, how many agents travel by bus every day and how many travel by bike every day? You could get that same output from a machine learning model that looks at patterns of how many people take the bus and the bike every day. But if you want to add some complicated sort of feedback loops and interacting patterns, then you could end up with something like an added rule that says if yesterday's commute was a success, I carry on following my normal rule. However, if yesterday I took the bus because it was raining in the morning, but then the evening was not raining and I was really sweaty on the bus and it was uncomfortable. If it wasn't raining when they set out and then it started raining really quickly, for whatever reason, they decide yesterday's transport was a failure, then they might copy the nearest agent who had a successful transport yesterday. Now, the nearest agent might have a different rule or might wake up at a different time, which means you get agents copying the behavior of people who are not exactly like them and therefore would behave differently. And you can get these weird, emergent, flowing, interacting feedback loop patterns of changing behavior that is not super predictable. It's really hard for us as people to predict how 1,000 virtual agents are going to react if they have rules like these. So that's just one potential difference in between a machine learning model and a sort of bottom-up agent-based modeling kind of output prediction for the same potential kind of synthetic data you might want to get about transport data. So before we get into the examples, I do want to take a little bit of a break, but there's a couple of questions. So have you ever used an agent-based model? We've got some yes, some no. One person has used loads. That's great. A few people are not sure, and that's fair because agent-based models don't look the same all the time. You might argue if you've played like Roller Coaster Tycoon, that might be an agent-based model. I'm not sure. I haven't really looked at that. But these kinds of video games use some of this same thinking, as in all the agents are sort of walking around bumping into each other and doing the thing. And they have rules about like, do they hit a wall and turn around and go back? Or do they hit a wall and keep hitting a wall? Like, yeah. So, okay, most people have not used agent-based models before. That is not a problem. We do have a couple of older workshops that we ran at least maybe 2 years ago on our YouTube channel. I think we did 3 one-hour workshops, one just on what agent-based models are, one on incorporating real-world data into agent-based model, and one on running experiments. You can find those if you want to learn more about agent-based models. Likewise, we have workshops about what is synthetic data. If you want to know more about it, more insight into the details, Emma's just posted a link to our synthetic data YouTube channel playlist. And then if you want to learn more about other generation methods. So we're focusing on agent-based models. That's a simulation method. There are other methods. Tell me, if you could build an agent-based model, or use an agent-based model built by someone else, what would you want to build one? Or what would it be about? Maybe the roller coaster tycoon sounds great. You want to build a roller coaster, a theme park agent-based model, maybe an ecosystem model, a traffic model, a model of how fashion styles change. Ooh, response to policy. That's a really good option. Yeah, definitely. Because some people will cheerfully follow a policy and other people will immediately look for how they can cheat. People joining queues. That is a really good one. Yeah, queues behavior and emergency response behavior. Those are really popular models, actually. Working at home, impact of governance, urbanization, geopolitics, healthcare, species propulsion, consumer behaviors, data usage, transformation, food policies, public sentiment shift. Yeah, that's a good one. Interesting. Very good. Food consumption, migration. I have worked with someone who did a migration model. So that's it. There definitely are some out there that you could definitely go have a look at. Household decision making, active transport, stress coping, leadership. Oh my God, you guys have so many good examples. Telecommunication networks. Yeah, networking models are also really popular. There's definitely some I can show you if you want to mess about with some. Census results, dynamic pricing. Those are really popular digital twinning models, energy and dynamic pricing. Good thinking, everyone. These are great. Student behavior, toilets, amazing. Social network structures, emotional responses, tax benefit microcircuit. Okay. Oh, fantastic. Okay. Um, Wonderful crime behavior. Yeah. Um, so we will look, I will, just to give you, before we go on break, I will give you a time to submit some questions. I will also look at some of the questions we've answered here. We'll answer some questions briefly, and then I will demonstrate some models live in NetLogo. I think I will have to stop sharing my screen at some point to switch over to sharing the NetLogo instead, but don't worry about it too much. But I will show some examples, and then we can take some more time for questions, and then I'll have up to 4 more models to show you, depending on how much time they take and how many questions come in. But in the first model I show you, it's a virus model. It's very simple. I want to show you the behavior space, how you set up experiments, how you generate output, and what the output looks like. Now, I'm going to demonstrate a virus model. Most of you should be able to download NetLogo. It is free. It is from Northwestern University, so it comes from a .edu website. So most managed computers will probably be okay with this. If not, you can probably talk to your IT department about getting it. It is a small package, so it will. I think it took me like 3 minutes to download and install. It's fast. It is free. It is educational. I recommend it. What you want to do once you have it, you can open, if you have a file existing already, you can open it. Otherwise, you can look in the models library, which is a big selection of existing models that you can play around with. I have this one open. This one is called Virus. What you're going to do is you're going to hit setup, and it randomly generates all these little happy little people. Well, they're not all happy. The green ones are healthy. The red ones are infected. You can put a slider to make the infection more or less infectious. You can have a slider to say what is their chance of recovery, and you can have a slider to say what is the duration of illness. You can also make them circle shaped instead of person if you don't like people. You can also, there's a slider for how many people, and there is a slider up here at the top for the speed. But let's just hit go and see what happens. Oh, look at them are all getting infected. There's some graphs over here showing you the numbers. There's also some tables at the top. I'm going to hit go again to freeze it. So we can now see that there are fewer green people, there are more infected people, and there are a bunch of gray people. These are people who are immune as a result of having recovered from an infection. Now I can adjust these numbers, hit setup again, and go again. And maybe it's a little bit easier to see. Look at that. This one, they healed completely. There are no red people now because there weren't that many infected in the first place. They all recovered. Everyone was fine. I recommend you play around with models like this to see if you can predict what's likely to happen. Obviously, if you have absolutely tons of people and it's really infectious and there's a really low chance of recovery and they're sick for a long time, they're probably all going to die. Let's just have a test. Oh, they're all red now. And oh, they didn't all die though. So now that there are no infected people, they will probably rebound and there will be lots more green people if we let it continue to go. Yep, the numbers are climbing. They're happily carrying on, not being infected. So there you go. My prediction that they would all die didn't happen because it turns out, am not very good at predicting what happens in agent-based models. And in fact, most people are not very good at predicting what happens in most sufficiently complex models. This isn't even that complex. There's 4 sliders and they go and that's it. But what's interesting for a synthetic data perspective is that under the tools menu, there's this little thing called behavior space. This is how we control the automatic runs of models. So if I click that, it opens this little window. And I have 2 experiments here saved, short and long. So the short, and let's edit the long, for example. This gives me the option of alternating between 10 weeks recovery and 20 weeks recovery. I can also change the name of the experiment if I want to. Let's just change it to big experiment, for example. You can change the number of people. The way this one's set up, it will start at 50 and increase by 50 in increments up to 300. Chance recovery, I decided not to change. The shape, I decided not to change. The infectiousness, I decided not to change. At each combination of these parameters, there will be 100 repetitions. And this is where I determine the output. So I want to know how many people are sick, how many people are immune, and how many people are neither sick nor immune. But I don't want that at every time step. I only want that every 10th time step, and that's how I define that here. The commands, set up and go commands, and I want it to stop running after 1,000. So if it stops running sooner, it will stop running sooner. You know, if they all die, for example. But if they're not dead at 1,000 time steps, it stops. So I can say, okay. And you can see now it's changed the name. Oops, didn't want to open that again. I just wanted to point at the name. But if I want to run it, run gives me this little window. And this is how I determine what shape my output is in. So spreadsheet is a wide output, so a wide format. Table is long. Stats is a overview. So it's not the same as every output. And list is just the details of the run. So not actually the metrics that I want. And then I can undo update view and plots because I don't necessarily need it to run while I'm looking at it. Parallel and 9, display parallel. There's a few features. So if I hit OK, remember this is 1,200 runs. It's, oh, for some reason it came over here in this window. I don't know if you can see this. It is on run 150 already. So it's very, very quick. Each of these is sort of taking, looks like less than a second to run. This is very quick. So I'm almost at 500 runs now in 26 seconds. This is much, much faster than actually corralling 292 people into a room and making sure that 6 of them start off with a cold and then measuring them every 10 time steps to see how many now have a cold. So we're on 900 runs now. I'm guessing this will take about 1 minute and 20 seconds. Maybe a bit less. Yeah, probably it looks like a bit less. So just over 1 minute to do 1,200 runs of 1,000 time steps each. Yeah, it's really very efficient. It took about a minute and 4. And what do we want that output to look like? I should have opened this earlier. Let me just let me get I think I'm sharing NetLogo rather than sharing my screen, so I may have to stop sharing. Okay, so why does that come up? Don't save. Okay, so at the top of the exported, so this is what you get when you export the results from an experiment. So it shows the run number here, and they're all jumbled up, although you can sort these if you want them all together. And it's got the step here. So at the beginning, they all start with 0. And then at step 10, they start giving some interesting answers. And, the results of what it's counting. So this is count with sick, count with immune, count with neither sick nor immune. And so, a lot of these things, you won't need all of these columns, but it gives you everything anyway. So this is long. This is the format that I like best because it gives you one row of data for each run that was, that was run and the results that were exported at each time step. So each run and time step combination. I will briefly show you, don't save that, the wide format because some people prefer wide. Why is it opening on a different screen? So unpredictable what it's going to be doing at any time. So in this one, it's just got them, it's basically rotated the other way. Oh, this one is lists, stats. So this one is the high level stats. So rather than giving you the reports of each run at each time step, it's giving you the statistics. So it depends on what you want your synthetic data output to look like. But you can see they're all different. Even though all of these features are the same, they start getting really, really different really, really quickly. And this probably seems very abstract. Do you have any questions on this part so far? Yeah, I will share the details of the books at the end. I think I have a further resources slide at the end of my presentation. I will go back to the slide deck right at the end. Do we have any other questions on virus model before let me open up the chat because obviously I've missed it. Can you seed the runs? Yes. One of the things, and I will point out how you do that in behavior space when you edit the runs. So you can measure runs. You can also say export seed. You would need to put it in your code that you record the seed, the random seed that starts a variable as a particular variable. And then in this experimental metrics, you would say print seed. Essentially, that is definitely something you can do. And if you do that and you use that seed, the runs will be precisely reproducible, replicable. So that is something you can do. Obviously, not everyone is interested in it precisely replicating specific runs, but maybe you do. Maybe, if nothing else, it's something that someone might be interested in, even if you can't imagine that it might be an interesting thing to do. Okay, any other questions on virus? No? Okay. So I'm going to show you how I want to discard the changes. I want to show you how a slightly different virus model is different in terms of how it looks as well as how it behaves. So now in this one, we've got all the same features from the first one. So how many people, what's the infection chance, what's the recovery chance, what's the recovery time. But in this one, we've got a bit more features. Let's see if I can zoom out. Yeah, a little bit so you can see this. In this one, there's a quarantine element. So most of the agents cannot cross the yellow barrier. but some can. So you've got these isolation average tendencies, hospital going tendencies, chance of inoculation, chance of ambulance, all these kinds of things. You can add more complication. And again, you can see that you get different kinds of behavior in the model. In this case, it stopped running because everyone was either inoculated or healed, I guess, or not infected. So let's have maybe more people set up go. And this time, oh, really, really, there was huge illnesses, but then a good recovery. So you can play around with these kinds of things. Any questions on virus before I move into other kinds of models? Um, yeah, you absolutely can create a new model from scratch. You would do that by File, New. It would come out very blank. I recommend you start. I mean, at some point, you will probably want to build new models. Someone has pointed out that seeds are important for some funding agencies. So absolutely, it's a good habit to get into to export your random seed. It's always good for reproducibility, for transparency. So it's a good point. So I will open up some other models that I have prepared. Flocking is one of my favorite ones. This one models some birds that start out in random formation. I mean, they're triangles, but pretend they're birds. And these sliders control how far ahead they can see, how far apart they like to be from other birds, how sharply they can turn, how much they want to follow other birds, and how these kinds of features you can find in the info button or the code button. You can find the info is like how it works, how to use it, what to pay attention to. In the code, you can actually mess about with it. So if you want to make them orange instead of yellow, you can do that. So when we go, the point here is to predict or think about whether you get one big flock or lots of little flocks. And you see them moving around, and at first they look really random, and then they start to say, "Oh, hey, there's a bird. I'll follow that bird." And you start getting these sort of lines, and then you start getting clusters. And it's really hard to predict how many clusters you will get, how big those clusters will be, what direction the clusters will end up clustering in. These are the kind of things that really influenced by this is an emergent feature of the behavior of the model. If I set it up and go again, they will probably end up going a different direction, even if I change no other sliders. We've got a question saying, will I demonstrate how to generate synthetic data based on real-world data set that originally contained sensitive personal information? I can't demonstrate that because that would mean showing on my screen personal data, but I can talk about it. We will talk about sharing synthetic data and end user licenses and how to deal with synthetic data that is generated using sensitive real data. So I will come on to that. Yeah. So someone else has asked, assuming we are working on a bottom-up system, there is a chance it can be simulated using these types of models. Yes, there is a very good chance. And it's important to remember we never know for sure that the real world works the way our model suggests it could work. But having a plausible and like data generating method of how to create that behavior is at least a good place to start for maybe observing the real world in new ways, building the model in new ways, looking for other ways to test or verify or compare the real world and the model, the agent-based model simulation. It is a very good way of trying to understand genuinely bottom-up systems and problems. So let's look at another model. Open. We'll discard that. It asked me to save because I changed the color. And it was like, ooh, do you want to save this? No, I don't care. So in one of the questions we had, we we talked about social, one of the questions that came up was about sort of social networks and like behavior like that. So this one is growth of a giant component. So in this case, we have just people. They're all standing in a ring, and we ask them, for example, look around you and form a network connection to whoever you happen to see. Now, we as people are generally not good at predicting which one of these people will be connected to who else in the network or how big the final network will be. And if you go once, oh, those two are connected. You go again, those two, we keep going. Already, some people have more than one connection, while lots have none. If we hit go forever, we see these big networks come and they start drawing people in and they start building shorter and shorter path lengths. And the giant component is the one in red. And we can try and make a guess of like how long until everyone is connected to the giant component or what the end result will be. Right now it's 59, 64 now. It's growing. It's a hungry guy, this giant component. And, really quick. And still there's people that have no network connections. So, this is weird, kind of unpredictable behavior. And there we go. It looks like almost everybody is connected. It won't be too long before this last person gets connected. Or will it? Oh, they're now connecting within themselves and they're just leaving this one out on his lonesome. Sorry, buddy. Oh, now he's connected. So there you go. In this case, this is a social networking kind of model. And this is about how connections are formed, how some people are really tightly connected while others are left isolated. This is it's addressing a different kind of bottom-up problem in a different way than the birds, but it's similar in that it is about the individual interactions that, just people ticking along doing what they do at their local level that create a large global level pattern that can be detected. One last one I wanted to show you in my pre-prepared, and it's called Rebellion. In this one, we've got, it's a little bit hard to see this one. Let me zoom out a little bit. So I wish they'd set this up differently so this could all be on the screen at once, but I don't think they were expecting me to have a monitor the size of mine. What this one is you've got a bunch of people and you've got some cops. And essentially, it's like, how many cops do you have to have in this neighborhood to prevent anybody from doing a rebellion? So the rebellion in this model is just like turning red, I think. But it's supposed to manifest as like how many cops to have to be present before somebody makes graffiti or throws a brick at a car or does something, against the rules. So let's run it. Ooh, we see the rebellions kind of spark and then die out and spark up and spread quickly and die out. And if we change them to maybe we'll have many more cops set up. Ooh, should not be greater than 100. Okay, well, why is it letting me do whatever? So let's try this one. So there's more comps and it's still running and we don't see those blooms of red where the rebellion sort of acts as a contagion and people start seeing rebellious people and they go, hey, I'll do a rebellion too. So this is another bottom-up system where the interactions of people who happen to be able to see someone else in their neighborhood change their behavior based on their personal history and what they happen to be seeing. So you can imagine that this applies in other contexts. For the fashion trends, for example, someone brought up mimicking crime behaviors when they talked about what kind of behaviors would they want to model. There are loads of very cool models in the models library. Discard these. And these are all models that are built in already that you can play around with in the categories of art, biology, chemistry, computer science. Someone earlier mentioned Conway's Game of Life. Why is it not life? This is a very cool model in which the cells just change color on what color their neighbors are. And it's really unexpected that, oh, let's go forever, that you find these sort of perpetual blinking things. These are called blinkers. And if nothing touches them, they'll blink forever. But you get these other things called glider guns where they move across the screen in predictable patterns and they can wipe out blinkers. And so, yeah, these really cool behavior based purely on what color is my neighbor that determines what color I will be. Let me take some questions. Let's see. Um, Someone is saying, thanks for the webinar. They've got to go. Absolutely. No worries. Um, the slides will be made available afterward, and the slides will contain all the things like recommended books and other sources. What are the main ABM outputs to report in the paper? How do you recommend report sensitivity analysis? These are really detailed. I would recommend, let me see if I have my book handy. I don't see it on my shelf right now. I've got too many books. Um, Stop share. I would say I co-wrote a book called Agent-Based Modeling for Socio-Technical Systems. And in that, I talk a lot about how to build models, how to verify models, how to run experiments. And there are several case studies of models in which people have identified a problem, built a model to address it, run some experiments, and published the research. So that is a really good, potentially good, useful source of information on like how to build models, how to run experiments, how to deal with validation and those kinds of topics. Let me go back to the slide deck because we are now at the point where I can deal with this. Let me share my slides again. Share my screen. Okay. So if you want to play around with any of the models that I have showed you, or any of the other models that are interesting to you, most of them will be available via NetLogo on the web. And here's some links to the ones that I showed you today. But there is the model library on the NetLogo on the web as well. If you want to make changes to a model or run experiments, you will need to download NetLogo, install it on your computer, and use that to change and run experiments. So let's briefly talk about the pros and cons of agent-based modeling. You don't need to be good at predicting what will happen in this model. So I was bad at predicting whether everyone would die of the virus or not. Don't worry about it. You can get the computer to run them all for you. And because you can look at the model code, you can really inspect someone else's representation of what's happening. You can look at the rules they use to decide to change color or to do the thing or to die or to get infected. They are quite cheap and easy and fast. It took me, a minute and 4 seconds to run 1,200 repetitions of a virus. I could not do that in the real world in a minute and 4 seconds. You can get impossible data. So that would be things like data about the Big Bang. We're not going to get real data about it, but you can model it, or data that is unethical to get in the real world. So maybe about how children adapt to abusive environments. That is unethical. As soon as you know there's an abusive environment, the priority is to get the child out of that, not to sneakily study them to see what happens. But you can build an agent-based model and test how it behaves and compare that to any real world outcomes that you were not able to intervene in and see if it seems to predict the behavior appropriately. And just as I was able to explain all these to you, they can be very easy and natural to explain. You can demonstrate the virus model or the Conway's game of life and say, look at these behaviors. Let me run it again and I'll show you. And people like seeing the visuals. They like seeing the time lapse. They like seeing how it goes. And people can really understand it and explain and identify with the choices and the actions. However, there are cons. So the same reason that it's hard for us to have good intuitions about what happens in the model means it can be hard for us to reflect critically, especially if we run 1,200 repetitions and it shows us that 5% of the time, absolutely everyone dies, and 95% of the time, everyone recovers and it's better. You think like, but why? So, do the best you can. Capturing abstract concepts is difficult, and putting them in code that a computer can understand and run may not adequately capture the abstract concept. That is a challenge. It's still worth doing, but you're always going to get someone who says, I don't think you've done it right. And they might be accurate. The results of agent-based models are either treated as truth because a computer has said so, or they are treated as nonsense because a computer has said so. And it's really hard to account for how people's concepts of what modeling and simulation and computer research does. It's really hard to deal with people who are like, it's true, therefore I will not think critically, or it's computer generated garbage, I won't even look at it. This is a challenge. It can be hard to verify, especially with impossible data. We are never going to be able to compare our model's results to the Big Bang. And no matter how much we compare it to lots of real world data, some people just might not find it comparable. So it can be hard to verify, it can be hard to validate, it can be hard to argue that this is meaningful. And it can sometimes be hard to use the results. So for example, if you run 1,200 virus simulations and 5% of the time everyone dies, it's hard to know what to do with that. Should we all wear masks because 5% of the time someone, like everyone dies? Maybe. Maybe that 5% is enough that we think about that risk is real and I will deal with it and it's fine. But not everyone is convinced, and it's even more complex sometimes. It's just a little bit difficult. Now, we've had a few people ask about sharing agent-based data. The output of an agent-based model or any simulation is synthetic. And in theory, synthetic data is very easy to share publicly. So you can share the model code, you can share the output freely if no licensed or personal or controlled data is used as an input to the model. That is, no one who looks at your code or your data can see the licensed or controlled or personal data within it. You should always check the terms and conditions of use for any licensed, controlled, or secure data that you are using. And if you have to use controlled or licensed data and you're not allowed to share it, you may consider making a synthetic dummy of it that your model will use as an input, because that way you can share the dummy data that is not used but created directly from the real data and the model code, and everything is synthetic. No data has gone into the dummy or the code. You can share that. The results that you publish in your paper that used the real input to your model, you have to say this is shareable under very strict conditions. You might be able to lodge it with the UK Data Service, for example, and say the real outputs from the model are only available under certain conditions. Please check your license. Talk with your ethics board. Make sure you're using and sharing data responsibly. Okay, there's lots of platforms. I've demonstrated NetLogo, which is here in the middle, because it has the built-in visualization, and that is lovely. However, NetLogo is not very powerful. It is absolutely powerful enough for me to have done all the research that I have done. But if I was trying to build a real-time energy digital twin of everyone in Birmingham, it would not be powerful enough. For that, you might want to use a more sophisticated one like Mason or Repast or EMLab, or directly an object-oriented software like Python. There are downsides to each of these in that they may or may not have visualizations built in. They may or may not be well recognized by other modelers. So the people might say, you wrote it in Mason. I don't know Mason. What do you? And they are not as easy to learn as NetLogo. NetLogo is very beginner friendly. That doesn't mean you shouldn't learn them, but it means maybe learn a bit about agent-based modeling in NetLogo first, and then build your real project work in a more sophisticated language. Here are some resources for more learning. So I definitely recommend Wikipedia articles. There are comparisons of agent-based modeling software. There is an article on agent-based models. Comsess.net is a lovely website in which people who have built an agent-based model lodge the code for that model with a repository freely available. And so you can look at lots of people's code that they have built for their real research. So you can look at people who've built like models about flood defense systems or viruses or transport or economics or migration, all these really cool research topics. Someone's built a model that's probably a bit similar. And so you can go look at their model and either use their model and adapt it for your purposes, or just be inspired by their model when you go to build yours. You can download NetLogo at northwestern.edu. There's also a dictionary of all the coding terms that you need if you're going to change the code or write your own code. And there's a tutorial series starting at here's a model, here's how you pull the sliders and push the buttons, to here's how you change the colors and, change all these features, to here's how you build your own model. And then I've got some contact details if you want to talk to me. I'm going to stop sharing the screen in just a bit and go to the questions. But I do want to give you a chance to take a picture or capture your screen or jot down these details in case you want to, for example, my name. You can search my name and you will get access to I think it's a Springer scientific publications book about agent-based modeling for socio-technical systems. If you need a copy of the PDF, I can send it you. Please email me. Okay, I'm going to stop sharing and go to the questions.